So welcome to another seminar for structural engineers. This time we're going to be talking about structural aluminium portal frames, and we look how we design the members and the connections to AS NZS 1664. So this is one that's specific to Australia and New Zealand, although there are some generic comments. The construction, well, this particular frame you may have seen before in a previous video. It's like a Meccano set. They are pre-formed extruded aluminium sections, and they're bolted together using steel inserts. And if they're very organized, they'll put all the bolts they need into different pots with labels on them, so they know which bolts to choose for which component. All you need is a telehandler to erect the frame because it's relatively lightweight and there's a lot of repetition. And before you know it, you've got a full building erected and braced on your concrete slab. You also require a elevated working platform to finish off some of the connections and to fit the roof. Having going on, and to see more of that particular frame, which is down in Picton, watch CPD seminar number 12, where I talk about construction monitoring and go into the details of that particular frame. This seminar is focusing on the design of aluminium portal frames. And the good news is that the design of aluminium portal frames is very similar to the design of steel portal frames. So if you're familiar with the design of a steel portal frame, this won't be completely alien to you. You're about halfway there. So this is our typical report, and a report that we do in Redco. Begin with a nice title page. In the contents, you'll see the typical information that we provide, including the PS1 and the design features report. We go through the loading and we go through the analysis for the frame, look at the results and do some member design checks and connection design checks, and on we go. I won't spend too much time going through this document as this has already been issued, but it's a fairly typical product of Redco. So importantly, we can do our wind analysis as normal as we do for a building. Now you could do it by hand, or you could use a piece of software. In this case, we've used CheckWind, and that gives you your wind pressures that you wish to design on your building. So roof pressures and wall pressures, and you can take that and add that to your analysis model. So we've modeled part of the building in this case, and we've used Bentley multi-frame, very simple frame with the end bay. The reason we do the end bay is because that's usually where the maximum loads are applied, particularly on the wind load side. Members and sections. So we have a same section for the portal rafter as we do for the portal stanchion. Here is the wind loading on the west of the building, coming from the west of the building. And here is the results of the analysis as displayed in Bentley multi-frame. And it's color-coded for the bending moments from a minimum to a maximum. So not surprisingly, your maximum bending moment is around about the knee. So here's an extract from the calculations that we've done for the member design checks. Click on that and open up the MathCAD. So here is the MathCAD for the design of the member of the portal frame, rafter or column. And we begin with putting in the input. In this case, we're taking the input from the multi-frame output, as it were. In this case, we've started with a table. This is a simple way of displaying inputs or variables in MathCAD. We could carry on with a number of rows, but basically the variable called n subscript c is assigned the value of 28.4 and so on. And then you can use that in your calculations which follow. Now, if you don't know the section properties, you can approximate, in this case, the section property to a hollow section. And so we put in the width and the depth and calculate the second moment of area, the torsional constant, radius and gyration in the normal way. This is where we're differing. We've got some mechanical properties which are derived from the aluminium alloy. And it's noticed that this alloy, which we'll come to in a moment, is not actually in the Code of Practice or the National Standard 1664. So 6082 aluminium alloy is an alloy that's been created since the publication of that standard. But the nearest equivalent, based on its chemical composition, is 6351, which is in the standard. But there's also another way to find out some of these parameters, and the values that they're given can be derived elsewhere. I'll come back to that in a moment. So in terms of the design of the aluminium section, we start with the buckling constants. So these are taken out of table 3.4 from the code 1664, and we derive some basic parameters which we will use later in our calculations. So let's start with axial capacity checks, and we start with tension. Tension is fairly straightforward because it's just the area multiplied by either the yield strength or the ultimate tensile strength. So whichever gives us the lowest value. So that's a relatively simple calculation to derive the tensile capacity of the column we're looking at. We then go on to compression, which is covered by clause 3.4.8 of the standard. For that, we need to know what the length is, and the unsupported length and unbraced length. In this case, we're looking at 5.3 meters. We derive some slenderness factors. So bear in mind, we are starting with the gross section. So this is the tube as it stands. We then put in the parameters for the slenderness, and there are three cases. And also, because we're looking at major axis bending and we're also looking at minor axis bending, we have to do it twice. We define the lower and upper bounds of slenderness, and these again taken from the standard. And these values vary depending on which your element has been used for, what function your element is being used for, and the load that's applied to that element. So we have three cases. If your slenderness is below the lower bound, you get one value. If it's above the upper bound, you get another value. And if it's somewhere in between, you get a third value. And so you compare the slenderness that you've calculated with the slenderness parameters, the upper bound and lower bound, to derive the actual stress that you're going to be using. And that stress is then used as a buckling strength, in this case in compression, and that will give you the capacity of the column in compression. We have to look at the components of the column. In many cases, the elements of aluminium sections can often be slender, and they can be the issue, i.e. you're getting local buckling before you're getting overall buckling. So we'll look at a plate. In this case, it is going to be the web. We derive the depth divided by the thickness. We give a slenderness value of 70 in this case. And now we have a different set of upper bound and lower bound slenderness values, so S1 and S2. And again, we've got three cases, and compare it with our slenderness value to get a value of 81.4 megapascals. So our member compression capacity is therefore the gross area of the section multiplied by these stress values. Now, although we're looking at a limit state design code, we still have the mentality of what's basically permissible stress or allowable stress. So because we don't actually get to the maximum yield stress when we're putting this component in compression, we limit the stress that we can apply. So in our case, we compare the capacity of the section with the applied load, and we're getting a mere 7% utilization. So that's not one of the problems of this section. We now go on to bending capacity checks, and we're looking again, we look at the gross section first. And again, we derive slenderness limits, S1 and S2. And our green squiggles say we've used these parameters before, but don't worry about that. And we've got another equation for the slenderness in bending when we're looking at the gross section. Again, we've got three cases, and we compare the actual slenderness with these limits and derive what's basically a permissible stress, allowable stress, or limiting stress to get our compression strength. And therefore, we then give you our section capacity in bending, in this case, at 94.1 kilonewton meters. We repeat the process about the minor axis because there's potential for biaxial bending in these components. Then we look at the compression in the components of the beams. So we're still in bending, but we're looking at the components. So it's the plates, the flanges, and the webs. We get a slenderness value of 30. Again, we compare that with the lower bound and the upper bound value of slenderness to derive the allowable compression strength to give us the member bending capacity. So we take the minimum of the local bending capacity and the overall bending capacity to give us a utilization of 77%. Then we repeat it all again in the minor axis. Then we look at shear capacity checks, and this is where we get even more complicated. We derive some buckling parameters because it's not just about plain shear, it's about shear buckling of plates. And I've hidden a little calculation here because there is a solve block. So the upper and lower bounds of the slenderness are not as obvious as they are for your axial capacity and your bending capacity. You have to find what your upper bound slenderness capacity is. And to do that, they say it's the intersection of these two equations. It's very complicated. Basically, you have two equations that equate to each other when the value of S2 is the same. Now, you could do it by trial and error, or you can use the solve function in MathCAD to use find S2 with an initial guess. If you're lucky, it will converge. In some cases, it doesn't always converge, but this is a relatively simple formula to solve. So we then punch that number into the equations and we find out what our shear strength is. So basically, it's another allowable shear strength, and derive our shear capacity. And in this case, shear is not a big issue. It's only 9% utilized. We then look at designed combined actions. So combined, in this case, axial load and bending, looking at clause 4.1. So then we derive the compression strength and the bending strength about the major axis and the minor axis, and derive what the applied axial stress is and the applied bending stress is. Again, major and minor axes. So depending on how big your applied axial force is, you use different equations. So in this case, we use equation 3, which gives us that equation. Now, it's gone over 100%, it's 104%, and I've cheekily said, well, it's okay because these combined actions do not occur all at the same time. One useful thing you can do in MathCAD is hide the other equations that you may need. So if your FA over FA, so the applied stress over capacity, is greater than the 0.15, you use these two equations on the right hand side here. So these are called in when we need to just drag and drop them into the correct place. Then we can look at combined tension and bending, and here we're right on the limit of 99%. Again, looking at clause 4.1.2 of the code. Sometimes shear and bending may be a problem, so you combine shear, compression and bending, looking at clause 4.4 of the code. And we derive our utilization as follows. So that was the member capacity check. And the reason we need to do that effectively by hand is because multi-frame and other programs don't have a design function for aluminium. Moving back, so just to focus on the material properties, as I mentioned, the section we're using, the material we're using, isn't actually then the standard. We're using an approximation of the nearest alloy, and then we've got some other values. Where have I got those from? Well, we can take it from a website, or we can take it from the standard. Here is the standard, and it's a mere 82 pages long, published in 1997, and probably due an upgrade, or at least a certain revision to it. It is a little bit different from Eurocode 9, by the way. So if you're familiar with Eurocodes, this isn't anything like that. So within the 1664 standard, there are these tables for the mechanical properties for the aluminium alloys. And as I've said, there are lots and lots of different aluminium alloys available. And it's not just the alloy you need to say, state, you need to say what the temper is. So that's the T6, T5, and so on. So you will also notice that the properties of these aluminium alloys vary enormously, from things that are really just used for cladding right up to structural materials. So in a similar way, when you're specifying steel, you need to specify the actual grade and the subgrade. You need, in this case, for aluminium, specify the grade and the temper, because the temper can change the section properties that you use. There's also a useful website. If you've not come across it, it's worth having a look. It's called Make It From. And so it contains a number of different materials. And we're looking at aluminium alloys. Select the series you're looking for. So A600, we're looking at the 6000 series of aluminium alloys, picking one at random. And that will give you the mechanical properties for that particular alloy, and they're pretty much all different. Interesting, this parameter, the elastic modulus, or Young's modulus, may be quite crucial because it's significantly less than the Young's modulus for steel. So aluminium, as you can guess, is a lot less stiff than steel. So if you're thinking of designing an aluminium frame just in the same way that steel frame, beware of this value, because your deflections will be significantly larger because of it. And because of that, your frame may be dependent upon deflection, it may be governed by deflection. So coming over to the connection design, we'll just look at one of them. This is the portal knee, which is usually the crucial section. In this case, it's a modular structure, and we're putting an insert into it. So we're back to MathCAD, and I've set up a MathCAD sheet for this type of connection. And it's a steel insert inside aluminium tubes, basically. And we're transferring a moment and a shear and an applied force. And you bang those in as an input. And the moment is transferred via the bolts. So we need to find out what the polar moment of inertia is for those bolts. So put in some basic input parameters. How many bolts have you got? How many rows, how many columns? for a grand total of 4 bolts. How far apart are they? Which makes a big difference. And then you get your polar moment of inertia from that. From that, you can derive the horizontal component of F. That's F, the maximum force in the bolt, and the vertical component of F. So you're combining the moment with the axial load for the horizontal, and in this case, the moment with the shear for the vertical component. And then you get the resultant, the vector sum. And then it's just straightforward. Here is the bolt, and here is the bolt capacity for that. You could have picked it out of a table, but you can derive it directly in this case. So the bolt capacity is only used up to about 41% in this case, so happy days. You need to check the plate materials, and so you look at the aluminium, that is the portal rafter, and the steel, which is the bracket inside the rafter. So you have 2 lots of materials, 2 lots of material properties. We're looking at bearing, first of all. And so clause 3.4.6 of the code gives you the derivation of the bearing capacity. In this case, we're sharing the load between 2 webs, which is just as well, because we're up to 78% utilization. In terms of shear loads, again, clause 5.1.2.3 gives you the equation for the shear capacity, and we get a result of 61%. And check on the steel insert resisting the shear. So you check on the shear in the aluminium and check on the shear in the steel as well. So you look at the bending capacity of the steel insert. So quite conservatively, I've just used the webs of the plates of the tube that's inside the tube, and we get to a maximum of 70% in there. And we do a vector sum to combine the 2 utilization factors. That's taken from equation 3.3.5. And that's the knee connection designed. So that is the end of that particular presentation. Looking forward in 2 weeks' time for something completely different. The next seminar will be about my personal journey all the way from the United Kingdom to New Zealand, and how I moved from being a C-Eng to a C-Peng, the transition from UK to NZ practice. This will be particularly relevant to those who are new to New Zealand and have come from abroad, and anybody thinking of migrating to New Zealand as a structural engineer. Just a reminder of the Daddy Pig YouTube channel. This is the place where these seminars are recorded, and there's now 3 playlists. So there's the original playlist of the CPD webinars for structural engineers, and we're starting from webinar number 2 all through to seminar number 22, plus a MathCAD for Dummies. The other playlist is the MathCAD for Structural Engineers, and we have extracts from those CPD seminars, short clips which focus on the MathCAD aspects. Just a reminder that the majority of my viewers are not subscribers, so it would be nice if you subscribed and hit that like button there. Share the show with your friends, and perhaps even leave a comment, as others have done.